the same time, it will be really useful for you to take it forward and to explore it further, right? So that's what I request everybody to go on mute so that it will be easy for me to continue. Um, I'm also going to play a lot of demos and stuff, so I request your silence, which will be really helpful for me. We are going to discuss two things today in this session. Can I have people on silence, please? Thank you. So today we are going to talk about two very interesting topics, which are very clearly the most important ones, perhaps the most frequently asked topics in the interview. If you talk about parallelism, yes, it's one of the frequently asked interview questions. Whenever you go for any interviews which are connected to embedded systems or computer architecture and organization or compiler design, this question will be there. So I will clarify what that is in a very neat way with some simple examples and explanation. I will also include some content, by the way, on the pipelining concepts, which are very important as well, which is closely connected to parallelism. So I'll give you some simple examples, and I have made it very simple, I believe, and you will like it as well, I hope. And followed by that, I will go ahead and I will show you two very important tools which are ruling the compiler world right now, optimization world right now. Dr. Shukanya, can you please ask people to be on silent mode?
Yes, sir, definitely, sir. Student, kindly put your mic mute. If anybody is polluting this, I will remove from link.
Hey, please, dear friends. So it is really tough for me to conduct a session when people are making noise. I hope you understand and agree to it. But please, I heard somebody singing. That's a nice voice, but still, we can listen to it at the end of the session if you're interested. And I will talk about two very important tools that are really ruling the world in terms of providing a lot of value add to the people who are working in the compiler area as well as in the area of design. So when you run a code, right, when you run a simple code or complex code or anything, you need to know where your processor is spending a lot of time. It should not spend time on something which is not important. So it's very, very important to know where it is spending time, where it is idle, where you can improve it. And also nowadays it is all multi-processor environment, right? So you are getting the code run, and there should be a system which can tell you like, this is the place, this is the content which can go ahead and get run in CPU. This is the content which can go ahead and get run in GPU. So this is called offloading technically. We need to know about offloading topics as well, which I will show you with two tools. One is going to be VTune Profiler, another one is going to be Advisor. Both of these are free. If you're working on some projects or if you're going to work on some projects in near future, you will be able to use these tools to understand if you have written a code which is good to go, right? Your code should not be just running. Your code should be running in an optimized way. Your code should be running in the best possible way, utilizing the CPU and GPU, right? So all these are going to be discussed clearly, and I will show you a demo as well as in how do you install, how do you run it. All these things will be clarified. And at the end of the session, if at all you have some questions, right, you can always ask me at the end of the session. I have also made this as a video. I'll share the video content with you as well so that you can go through it whenever you are free and whenever you require. I believe that it will be a useful session. I hope I'm clear and audible. Let me go ahead and share the content which has been readied purposefully for this session, and I'm sure you will like it. Give me a second. Dr. Shukanya, you need to confirm if you are able to listen to the audio.
Yes, sir. Yes, sir. It is clearly audible, sir. No issue. Yeah, video.
Let's start learning. We are going to
Yeah.
discuss a very important topic, parallelism. And this is a very interesting discussion. I will walk you through what is parallelism, what are all the types of parallelism available, how important is pipelining, what are all the drawbacks or the hazards that are connected with pipelining, and then what exactly is instruction level parallelism. All this will be explained to you very, very clearly. And followed by that, we are going to also learn a couple of tools. A tool like profiling tool and optimization tool is very, very important for a guy who is working in compiler design or computer architecture sector. So I'm going to introduce you with a couple of open source freely available tools like VTune Profiler and Advisor. You can use that by installing it locally in your machine, and it's going to be simply awesome. So the session is now described into two halves. The first half is going to be parallelism related. The second half is going to be related to the tools that we are going to see. It's all going to be practical in the second half. The first half is going to be with a lot of examples and real-time references. So I'm sure and certain that you will enjoy the session, and I will take up the questions at the end of the session. So if you have any questions, please keep it reserved for the end of the session. We'll open the discussion at the end of the session, and I can definitely take it up, and I'm sure you will enjoy the session. Let's get into the content right away. What is parallelism? Types of parallelism, instruction level parallelism, advisor, retune profiler, followed by Q&A. This is the entire agenda, and I made it very simple. So if you have any questions at any point in time, make a note of it and we can discuss that at the end of it without fail, right? Let's get into the content. What is parallelism? Simple. It is nothing but compiler design technique and processes which are designed to execute operations which can be like load and store, the integer addition, the float multiplication in parallel to improve the performance. I'm going to do the operations as the load and store, addition, float multiplication. All these can happen in parallel. I'm going to do the things in parallel so that it can improve the performance of the processor. Simple thing I can tell you, I'm getting 3 tasks right now to be done. So if I do all the 3 tasks in parallel, that is called parallelism. That's all, right? So it is a design technique. That's all. The processor will execute the operations, which can be any of this. It can be load and store. Load is moving into the register for the operation. Store is getting out of the processor after the processing the operation, and then after executing it and then pushing it onto some location for storing it. Integer addition, float multiplication, all these can be performed in parallel, and that's what is referred as parallelism. Can we take a simple example to understand parallelism better? Yes, we need a human way of doing it, right? We need definitely understanding here, and that's what is going to be explained right now. You are going to be given a very simple example with respect to vision. We are going to connect it. You are seeing a bus. What are the things that you will see in parallel? You will see the color, you will see the shape, depth, and motion all at once. Remember, you are going to see color, shape, depth, and many other features of the bus all at once. If you had to see all those things only one at a time, for example, first time I see only the color, second time only I see the shape, third time only I see the depth, fourth time only I see the motion. If I keep doing it, it is a disastrous way of doing things and it would take real long time. So we are having the capacity to see all at once, and that's what is called as parallelism. Simple. We are gifted with the natural parallelism ability for us with this vision. So what do I mention here? Very simple. Do multiple things in parallel. And bus is the simple example. You are seeing somebody, you are seeing everything out there in one shot. You are not seeing first the eyes, then the ears, then the nose. Not that. We are seeing completely as a human. We are seeing what kind of dresses they are wearing. We are seeing if they are carrying the laptop or not. Do they have the phone or not? All these things come into our view, come into our perusal right in one go. And that's what is called as parallelism. There are 4 types of parallelism that you must know. The first one is data parallelism, second one is bit level parallelism, third one is task parallelism, and the fourth one is instruction level parallelism. Out of which generally people will be too much dwelled towards the instruction level parallelism, and that's very important too. This section is an important interview question discussion area as well. They may ask you in the interview what is parallelism, and you may have to explain whatever example I have given you. Along with that, if you can give a technical example, that's going to be great. And you are going to then explain the types of parallelism, because that will be the follow-up question. So you need to talk about data parallelism, bit level, task parallelism, and instruction level parallelism. I'll explain you all these one after another in a very neat way. Followed by that, we'll go in depth into instruction level parallelism, and pipelining will be connected there with some excellent examples. I'm sure you will like it. Well, what is data parallelism? Data parallelism is all about concurrent execution of the same task on each multiple computing core. I am going to go with concurrent execution. The term is very important here. Concurrent execution of the same task on each of the multiple computing cores, right? An example would be very easy for you to understand this concept. I'm now taking a single core system. Now what I'm going to do is I'm going to sum up the contents of an array of size n. I have an array of size n, and I am going to sum up the contents. Now for a single core system, I'm taking a single core, not a dual core. I am taking a single core system. one thread would simply sum up the elements starting from 0 and it will go on till n minus 1. This is for the single core system. But when you come to the dual core system, a thread A could be running on the core 0. It could sum the elements from 0 to n by 2 minus 1, and parallelly thread B could be running on the core 1, could sum up the elements, rest of the elements. So what happens? Two threads would be running in parallel on separate computing cores. This is called data parallelism. This is a very important concept. Data parallelism is all about concurrent execution of the same task on multiple computing cores, right? So I gave you an example. There is some addition example given here. First half would be done with one core, the second half would be done with another core, and this is called as data parallelism. Now the next one is called bit level parallelism. What is parallelism? I explained you. Doing multiple things. We see a bus is the example. What is data parallelism? I have an addition operation to be done with a array, and I am doing the first half in one core, I am doing the second half with another core, and I go with data parallelism through this approach. And the next one is called as bit level parallelism. This is a very important type of parallelism. This is a form again of parallel computing which is based on increasing the processor word size. I reiterate, this type of parallelism is completely connected with processor's word size. What is the connector? How is it going to help? I'll explain you this clearly. In this type of parallelism, what happens is, with increasing the word size, reduces the number of instruction is the logic. I am going to increase the word size, which is going to reduce the number of instructions the processor must execute in order to complete the operation, in order to perform an execution. So, greater the size of greater the length of the words is going to be better. So I am going to increase the word size, and it will in turn reduce the number of instruction requirements, and that's to be explained with an example. I am going to give that right now. We are going to take a simple case where we are going to take an 8-bit processor for an instance. This 8-bit processor must add two 16-bit integers. I reiterate, the 8-bit processor must add two 16-bit integers, right? The first lower order of the 8 bits, the first 8 lower order bits from each integer first will be added, and then we will go ahead with the 8 higher order bits, and then two instructions are needed here to complete single operation. I take the lower order 8 bits, I take the higher order 8 bits, and here we are forced to go with two instructions for a single operation which could be avoided. Now what did I say in the beginning? I told you that with the increasing the word size, with the increment in the word size, you can reduce the number of instructions. Now in this case, I have an 8-bit processor where I need to add two 16-bit integers. So I have to eventually increase the number of instructions because of the requirement. Now what I do, a processor with a 16-bit would be able to complete this operation in a single instruction. This is called bit level parallelism. You are increasing the word size. So that's very simple. Understand that point. Now, task parallelism. What is task parallelism? Task parallelism is very important. Task parallelism means concurrent execution of different tasks. Concurrent execution of different tasks. Earlier we were speaking about the same task. Earlier we were discussing the bit level. Now we are going with the task level parallelism, where we are discussing about the concurrent execution of the different tasks on multiple computing cores. I have multiple cores available with me, and we are going to establish the task level parallelism through the concurrent execution of the different tasks on multiple cores. I have multiple cores, different tasks, that's the connect. Now we can have a simple example here. I'm going to take two threads. Each is going to perform unique operation on the array of elements. Each is going to perform unique. So I have got two threads. One thread will be doing some unique operation. Another thread will be doing another unique operation. Now these threads are operating in parallel, which are operating on separate computing cores, but both of them is going to perform unique operation. So I have two persons working with me. They are going to do two different tasks, and they are two individuals, different individuals. That's exactly called task parallelism. I do two different tasks. I repeat, task parallelism is nothing but concurrent execution of different tasks. I reiterate that I put a code there. It is different task on the computing cores, right? On the different computing cores, on the multiple computing cores. That's what is called as task level parallelism. This is a very important concept. Do not forget it. This question, particularly in the interview, if you are attending something with processor related, or if you are attending with computer architecture or compiler design related, this question is quite prominent. So please understand what is task level parallelism. And next we come to is instruction level parallelism. What is it? We are going to go ahead with simultaneous execution of multiple instructions from the same program. I have got 5 lines in the code. If I can execute all the 5 lines at one shot simultaneously, I call it instruction level parallelism. That's all. Sir, I have heard of pipelining. Is it related to pipelining? Yes, we will connect that properly. Hold on until then. So we have discussed different types of parallelism till now. This is the one which is most important and most prominent as well. Instruction level parallelism is all about simultaneous execution of multiple instructions from the same program. I have got one program, it has got 10 lines. If I am capable of executing 7, 8 lines or 10 lines or whatever, based on the levels that we can go ahead with, if we can execute that parallelly, simultaneously from the same program, it is called as instruction level parallelism, right? Pipelining is a form of instruction level parallelism. Naturally and normally we are all going ahead with pipelining, and we are extracting as much as we can through the pipelining to get the instruction level parallelism at the best level. So pipelining is a form of instruction level parallelism. Remember it. Instruction level parallelism will enable you to go ahead with execution of simultaneous execution of multiple instructions from the same program, and pipelining is one of the ways to achieve this task, and that's coming under instruction level parallelism. Is it clear till now? We discussed 4 types of parallelism. First one is data parallelism, second one is bit level parallelism, third one is task parallelism, and the final one that we discussed is instruction level parallelism. I've given examples for all of this, and till now I believe that is very clear. So we are going to dive deeper into it, right? We need to know more about instruction level parallelism. Remember, from 1985, from the time the process started evolving, right? Pipelining was the major concept that this processor makers used to overlap the execution of instruction and to improve performance. There was no major option available by then. So pipelining was there from 1985. Remember, whenever I wanted to go ahead with simultaneous instruction execution, I go with pipelining. It is from 1985. So the potential overlap among the instructions is referred as instruction level parallelism, and pipelining helped us to achieve this instruction level parallelism. So when it was introduced, this was first introduced in IBM Stretch 7030 was the model number. In 1959, way back in 1959, this was introduced, and then later on it was evolving much faster than expected, and now we have multiple level pipelines available with multiple levels of support available for the instruction execution in parallel, and it provides better results also. So CDC incorporated pipelining and the use of multiple functional units that happened later, and in any questions, students? Any questions? I heard somebody shouting. So if there is any question, please open up. I will clarify.
Sir, just now I muted all because some students are doing some wantedly unmute and doing that. Anyhow, this session is recorded. We notice those people and we'll take severe action, sir. Don't worry, you proceed, sir. At the end, you ask questions, sir. If they ask doubt, if they have doubt, they can ask in the end, sir.
Thank you. I'll have to make it 200 only. This period will be wasted, but still that is fine. So this is the period that is getting wasted. This is the period that is getting wasted. Here we completed, so I did not have it here. I complete the 100 seconds here. I mean, I complete the writing process here. Here it is. So learn this way. When I'm going to read, it has to happen from the right. When I go into write, it has to happen to the left. So you can see that here, this is writing, this is writing, this is writing. So I fill the content to the left and I cut this part. But when I am reading, I need to move it here, and the first 100 seconds, the first period, first half should be left empty. So remember this is very important, and we will have more examples on this pattern. So if you cannot understand right now, don't worry, we will explain it again. The point is simple. Every block will be 200 because 200 is the maximum of the duration, and I'll have to go with 200 for each of the stages. So the worst case, if you see, the amount of time that we have spent is not more than 1300 seconds, 1300 picoseconds. Earlier, it was 3200. Earlier, we considered the longest of duration for the instruction itself, and we had to allocate that. Now, we are going with stage wise, and we are just picking that particular stage, and we are allocating that time to accommodate all the stages properly. That's it. Now, the point is very simple. When you go with pipeline architecture, the time required is definitely lesser. The time required is certainly much better than the time required for a single cycle design. Now, let's go with the formula. We need to understand the formula, and we need to understand how do we calculate the time between the instructions. Time between the instructions for pipelined architecture has to be calculated by the time between the instructions non-pipelined by number of pipe stages. That's all. This is how we need to use, and we will use this sometime later. Just remember this formula. For me to calculate the time between instructions for pipeline stuff is nothing but the time between instructions in the non-pipelined architecture by number of pipe stages. That's it. You will remember, you will have to remember this, and we may use this sometime later. Till now, do we have any questions? I will be happy to take up the questions.
Sir, 1 minute, I'll
Right, all of
unmute
you
them.
please go on mute again. I hear some echoes. Right. So let's go into the next topic, which is very important. I'll introduce you to the topic today, and we will go ahead in detail by tomorrow, because again, it needs a lot of time. I'm going pretty slow. We will understand this very clearly over a period of time. I am telling you, right, pipelining, if we complete, we are almost done with the subject. It's so very important, and it's very interesting as well. So make sure that we guys spend a lot of time in understanding all this properly. What is a hazard? Okay, I am the person A. I am trying to complete a distance of 1 kilometer by walking, and this is the destination. This is the destination. In between, there is a big pothole on the road, so I cannot travel. I am stopped at 500 meters. Now, this is a hazard. Do you understand? A hazard is something which is not letting me go to my target, which is not letting me reach my target. That's all is called as a hazard. A hazard is nothing but which can stop us to go to the next stage. That's called hazard. Remember it. Now, with respect to computer architecture, with respect to pipelining, we need to understand what is a hazard. Pipelining and hazardous situation is a very famous scenario and very famous and very common interview questions. So please listen to it carefully. If at all you do not understand, I will be able to explain you again. If you understand it at first shot, I am very happy. Let's understand. What is it? Very simple. In pipelining, there are 5 stages. Stage 1, 2, 3, 4 and 5. Likewise, for every instruction it happens. If the next instruction cannot be executed in the next successive clock cycle, I call it a hazard. I have got first instruction. The first instruction 5 stages are there. I have got the second instruction like this. I have got the third instruction like this. Now what happens is, if this cannot be started while this is being done for some reason, I could call it a hazard. If this cannot be started while this is being done, I could call it a hazard. Anything which prevents you from getting the navigation done to the next stage is called a hazard. Do you understand that? A hazard is something that stops your progress. We call it hazardous, right? Don't watch TV so much, it is hazardous. Don't be in FB so much, it is hazardous. Just like that, we are calling this hazardous because we are not able to move to the next successive step. That's it. Now let's get into the point very simply. There are 4 types of hazards. There are 4 types. Remember, all these are very important, and we are going to go step by step. The first hazard that we are going to learn is called structural hazard. The first hazard is called structural hazard. The term, when it calls a structural, you could have by now understood that it is related to hardware. Whenever we have something called a structural hazard, close your eyes and determine that it is a hazard which is connected to hardware. That's it. Now, let's understand the term further. The structural hazard is something which is going to not let you do the next step, but
This will happen because of a hardware malfunction or a hardware unavailability or hardware incapability. I can call either of these terms properly, but it is dependent 100% on hardware and it is going to stop the progress. Right. When the hardware is not capable of supporting the combination of the instructions, when the hardware is not capable of supporting the sequence for the flow of instructions, I call it as hazard. And this type of hazard is called as structural hazard. I'll tell you an example so that you can understand. Let's take the washing scenario that I told you some time back. There are two separate equipment available in the previous case. I have got equipment 1 and equipment 2. Once this is done, I threw it into this so that the next person started using this. I mean, I have got two instructions. I have got two separate hardware available. The first instruction used the first hardware, then it moved to the second, and then the second instruction started using. This is what I told you some time back, and I'm pretty sure that you guys remember it. Now, if in case these two are not separate and they are in the same box, they are in the same unit, the washing machine and dryer are together available as a one unit. Now what will happen? Until both the stages are over, the second instruction cannot use it. Do you understand the point? The first person will be using the washing and he will immediately use the dryer section of it. Though the washing machine is not being used, he is still using the dryer which is attached to the washing machine, and hence he is not letting the next instruction execute. The next instruction has to wait until such time both the units are available, because both the units are appearing as one single unit. Remember it, it is all about getting the availability of the hardware resources. Though they are available, if someone is occupying it and someone not leaving it, it will become a hazard. I'll tell you an example. The first person has finished the washing. He has completed the washing process, but he went for a phone call. He attends the call and he has forgotten to take the cloths out of the washing machine. There are separate units available even then. He has forgotten to take the cloths from here. I cannot lift his clothes and I cannot keep it somewhere. It is not my duty, right? So what will happen? The second person will keep waiting until the first person is back from his call to lift the material. This is a hazard, and this kind of hazard is called the structural hazard, and you cannot get pipelining done easily whenever you have this kind of hazards. So remember, this is 100% related to hardware. Whenever the hardware is unavailable or whenever the hardware is locked with one of the particular instructions and it is not releasing it for the next one to use, we call it structural hazard. Remember it, it's a very, very important question in terms of interview as well. What is structural hazard? Now, we need to understand one very important point. I'm going to give you a simple example and we will go ahead with the next hazard, or we'll go ahead with the explanation of further things very clearly. Now, the risk versus risk difference we have seen. MIPS naturally supports pipelining. MIPS naturally supports pipelining, and instruction set is constructed in such a way that they enable and they support pipelining. Listen to this point carefully. MIPS is a risk architecture where MIPS naturally supports pipelining concept, and this pipelining concept is enabled through the instruction set construction itself. So they have taken extreme care to make sure that the stages are constructed properly, the stages are curated properly so that the pipelining can be enabled. Now, we will assume that we are having only one memory unit. We are having only one memory unit and we are not having multiple memory units. I mean, dual memory units are not available. One for instruction memory and one for data memory for an instance, and we do not have it that way. We have only one memory. Now what happens? Let's assume this same scenario. When the first instruction is executed and when memory is accessed in the first instruction in the fourth stage, the fourth instruction will also need to fetch the memory, access the memory to fetch the instruction. So the instruction fetch, if you see that the instruction fetch and memory are colliding. Here I am trying to access the memory, here I am trying to read the instruction, both are in the same content. So here comes the problem. This is dangerous. So this is called a hazard, and this hazard has to be avoided, and this is called structural hazard. Do you understand? I cannot access this and this at the same point of time if I do not have two different memories. So without distinct components available for me, I cannot go ahead and look for pipelining. When you want pipelining, make sure that you have distinct components available and make sure that they are all available for rest of the stages to use it. The moral of the story is very simple. Whenever you go for pipelining, whenever you want to be done with pipelining, it will be expensive. Keep components separately. You need to have individual components, and there is no other option available. Use individual components. The next one is data hazard, which we will see tomorrow. I am going to explain you the data hazard clearly with lot of examples, and this is the best part of your learning, I am telling you. Tomorrow will be very nice, and this is called as bubbling. I'm going to explain you the complete data hazards only tomorrow, and day after that we'll go with the control hazards. And if you learn the control hazards, then we'll go to the pipelined data path. This is the most interesting part of your entire subject. I believe if you can understand all these properly, you can choose computer architecture as your favorite subject in your next interview process or your internship process applications, and that is that much interesting. Any questions till now? Hello. In this session, we are going to install, use, and learn how Intel Advisor can be used for vectorization analysis. You can boost your application performance like anything, and this tool is a phenomenal tool. This comes as a part of Intel One API, and in this session, we are going to walk you through, and every bit of it will be very interesting. In today's fast-paced computing landscape, if you see, optimizing application performance is the most paramount, and developer is actually oriented and developer is fully thinking towards optimizing the application performance. One of the most crucial aspects of the optimization is vectorization, which enables parallel execution of operations on multiple data elements simultaneously. This is a very important point to understand. The crucial aspect of optimization is vectorization, and that enables parallel execution of operations on multiple data elements simultaneously. By leveraging the vector instructions, applications can achieve significant performance gains. You can really see this, and this is really very wonderful tool which will help you in understanding how the performance gain can happen, where it can happen, how you can analyze. All those things are going to be very clear with this excellent tool. The Intel Advisor is a powerful profiling and optimization tool that comes to the rescue by providing the developers with actionable insights. I repeat it, actionable insights into the areas of their code base where vectorization can make the most impact. This is a step-by-step guide, as I already told you. We will walk you through the process of installing Intel Advisor and utilizing its capacities to analyze a very simple sample application which comes by default with the installation. Whether you are a seasoned developer or just getting started, it doesn't matter. This guide is created with an intention of giving you the complete necessary knowledge for you to identify and optimize the critical sections of your code where vectorization can yield substantial performance improvements. So let's get into the session right away, and this will start with the installation process which you can follow as such. So this is all very easy. Please follow the guidelines as I have given, and most importantly, you follow the description section. This is the page where we get the installation guidelines, as well as you can download it as part of the OneAPI toolkit, or you can go ahead with the standalone version, or you can even develop in the cloud. So we are going to use it as a standalone version. You can do multiple things with this tool, as I already told you, and today we are going to learn how vectorization optimization can be done with it. Rest of the things we will see in the near future. We have already downloaded it. The installation is going to be very, very easy, so follow it up. Once you have downloaded, you get sample files coming along with it. You can see the path where everything gets installed there. This is all given clearly in the description. You could see that we have got VEC underscore samples here. This is available by default when you download. I have moved it into a different directory, and I am going to extract it from the write permission available directory. So once you have this in your directory where you have got write permissions and no issues with respect to writing it, all those things are going to be really helpful for you, and you can then send that built application into the file, into the advisor for you to get inputs about where you can optimize. That's what I'm going to do right now. You can see that all these files are available. The next step is to build it. I'm going to launch the one API command prompt, and that is available right in front of you right now. So it's getting initialized, and it may take few seconds for you to get that done, but it doesn't matter. It's really worth the wait. So you are getting into the directory where you have copied that and you have extracted that. Now you're going to build it. Build.bat space baseline. So you are building it, and you can see that after you build it, you will get the exe file available for you, which you are going to send as the input into the advisor. bec underscore samples.exe is available. Now when you run it, you will get the output for the code. So the code is a very simple code, and you can try exploring that as well. This is from the samples, so you can explore it at your free time. So it gives you the result, execution time, gigaflops, everything is presented. Now let's send it into the Intel Advisor, and I'm launching the Intel Advisor right now. You can launch it from the command prompt, or you can go ahead with the GUI way of doing it as well. So advisor-GUI is the command that I need to issue, and the moment you issue it, you get the advisor launched. So create project is the button that you need to click. This is really exciting. Give the name there, whatever you like, you can give the name there. And once you give that, you will be able to select the executable file, the application that you want to send in into the system, into the advisor for further analysis. I'm selecting that right now. I'm going into the right path, test, as you have seen earlier. Inside that, I have got BEC samples, and there I have got the application available for me, which is available after the building process. Once it is selected, you need to ensure you go to the trip counts and flop analysis, where inherit settings from survey hotspot analysis type is selected. It must be ticked. Similarly, the same option under the memory access pattern analysis should also be selected. Just click OK and run it. That's it. Sit back and relax. You will get the results right in front of you, which will let you know more information about the code that you have written. You can understand your code better. You can understand where you can improve it better, and you can go ahead with vectorization and code insights, CPU memory roofline analysis, threading, GPU roofline, offload modeling. Everything can be analyzed, but this session is restricted to vectorization and code insights. Now I am going to click that, and I am running it. You can see that it may take a little bit of time. You do not have to worry about it. You can really get a lot of information after this wait. It takes a little bit of time, and after that you get plethora of information in front of you, which are really very useful, and you'll be stunned to know about all this information. That will help you in optimizing your system better, optimizing your code better. So it's getting loaded now. You can see the time elapsed detail, the collection started, and you will get all the information right from where the optimization can happen, vectorization details, why vectorization has not happened. All this will come in front of you. We will see that right here. Yes, we have got that. The source, the top-down detail, the code analytics, the assembly, recommendations importantly, why no vectorization, all this information are given to you. When you go to the code analytics, you get the details about the time required, the total time required, memory, compute, mixed, the details about the stats about all those are being presented. You are also getting the CPU time, and the time in the scalar mode is presented. Vectorization is not available here, as you have seen there itself. And you can see that we've got recommendations available there, which you can go through. So this is such an amazing information that you are getting at very little amount of time. That's going to be really helpful for you to understand your application better. You can improve the application. End of the day, optimization is what is required. You can see that the recommendations are presented here. You read through that step by step, where you can definitely improve the application's performance if you go ahead with the higher ISA, which is going to be done as one of the very important components. You need to remove the ambiguity that is going to be connected to the pointers. That's to be also done. Why no vectorization gives you some more details, where you'll be able to understand your code better, and how you can bring in vectorization also will be presented. So all these are really interesting, and the next option is going to be explored right now. I recommend you to try it once, and you read these through once, so that you'll have a complete picture of how things work here. So this may take a little bit of time for the first time for you to understand, but when you go through this, it will be really useful. You can see that the top-down approach with respect to the memory, with respect to the performance in terms of performance is presented. So the assembly language code is presented here. You can even save this. You can take a snapshot and save this. Some of the instructions could be very familiar to you if you're already using microprocessor or the INC, the compare. All those are typical instructions that we must have used in our early stages, and that's what you are seeing in front of you. Now I am saving it by clicking the snapshot option, which is available in the left hand side, as you have seen. I can save this kind of information for me to go ahead and read through the assembly language equivalent of whatever code you are writing, and that will help me understanding my architecture better as well. So I'm doing that right now. I'm saving this for my future analysis. This option is also a very appreciable option that we give you through the Intel Advisor. The next very important option that you need to know when you are compiling is the no alias option. When you are building is the no alias option. You must have come across situations where you could have seen that two pointers or more than that is pointing to the same memory location. Is it a mistake? No, it's not a mistake, but still you can avoid it. So if you are very sure that you have not done this aliasing, during building itself, if you convey it to the compiler, and when you build it that way, you get a new exe file and it is generated properly. Now I'm going to do that right now. Build.bat space no alias. So I'm telling that I have not used any pointer, any two pointers pointing to the same location, and I am now going to feed it as input into the advisor. So this new generated file, the new exe file is given as input, and now you can see that there will be a tremendous improvement in the performance, and this is a great option that we have in hand. Now that we have run it, we have selected that and we have run it, you can see that the results are going to be available for you. Only thing that we need to know is I have built the entire application, entire code with no alias option. You will see the improvement in the time. I'm going to show you that as well. So the code analytics is going to be presented. You can see that it's much lesser time than the past. Last time it was 5 hours, now it is 3 seconds. So there is a lot of improvement. And in summary, there is a beautiful thing which has been included. We have got vectorization happening here. You can see that the orange color highlighted things are revealing you the vectorization. So this is the best part of it. So you are enabling vectorization, and Intel Advisor gets you those insights as well. So we have got the top time consuming loop details, we have got recommendations, we have got the survey and the roofline analysis, and again you have got the no vectorization details as well. Why these areas have not got vectorization, why no vectorization in this particular region, all this kind of information can be available for you. Recommendation, I recommend you to go through it again whenever you are trying it out. There you will get a lot of insights as in how do you improve, where you can spend a little more time to improve things can all be seen. You can see that the highlighted data is giving you a lot more inputs. Well, we are getting into the next option. We have another option when you are building build.bat space xhost option. If you will use higher instruction set architecture. So you are compiling it and you are telling that we are going to use higher instruction set architecture. Now we have fed it as input into the advisor, and you are going to enable the flop option there, the trip count option there, and it will give you more information. And I'm going to run the tool for us to get better insights. This may take a little bit of time. Sit back and relax, and you will get phenomenal amount of information, and you will see the way the optimization has happened in terms of performance, in terms of speed, all those things. This is all amazing tool. I simply recommend you to go ahead and try it out. And once you get this, you'll feel really happy that you've got a tool like this, which is giving you a lot of insights. Here you go. You are getting the finalized data available for you, which is the clear insight, and this will help you in understanding where how optimizations have happened. The code analytics tells you that clearly there is an improvement in times of execution time. It's 2.4 seconds. That's what is needed, and you are getting the result right in front of you. And you've got a roofline analysis results also, which is available in front of you. Average strip counts details are available. You've got a clear summary which reveals the vectorization details, and this is a clear bit of information that can help you understand where how things go right, things go wrong. Recommendations will help you understand where you can improve it. All these will help you. Go ahead and try it out. The description section will help you in getting these things done much more easier. If you have any questions, doubts, you can always reach us out. Try out all the options, and it's fun. Thank you. We are going to install the Intel vTune profiler here, and it is a very easy process and a smooth process. We can install it as a standalone version, and it is going to be very easy for you to use it. The link is highlighted there. You can download the installables from there, and you need to select the operating system which you want to use. I am using Windows, so I need to select the installer type as well. You can go ahead with online or offline. You can read through the materials that they have given, the pointers that they have given, and I'm going to click download. It is a customizable installation as well, which I will show you. Once the exe file, I mean the installer is downloaded, you can double click that and it will start the installation process. It is very smooth, easy. You can sit back and relax for a few minutes. It will be installed. Automatically the system requirements will be checked, and in case of deficits, it will let you know what has to be installed, and you can carry on with that installation as well. So now the 1API is launched and Intel vTune Profiler is getting into it, and you can see that what are all the things which we are installing right now. We are installing Intel vTune Profiler, and we are going to accept the terms and conditions, and it is going to get integrated with the Visual Studio. I am giving consent for the data collection. It is up to you. And now there may be a reboot requirement at the end of it. Click install and it will go on. It will take a little amount of time, like 10 to 15 minutes it may take for you to complete the installation. It is about 680, 690 MB file, so it may take a little bit of time for the installation, and you can sit back and relax. Automatically the checks will happen. Automatically it will see if things are all installed fine. So please do not interrupt the process. It will keep going and you will get the vTune Profiler installed for you in a while. So you can wait for the installation, and once done, you will be able to open the vTune Profiler as an application. You can see that right in front of you. We have got it installed, and I am clicking the finish button. The moment you click it, you will be also provided with the link to the guide, the user guide, which I'm scrolling through right now. I strongly recommend you to read it through. Now what I'm going to do is I'm going to open the vTune Profiler, which has been installed in my machine, and we will start with analyzing and understanding how it is going to be useful for us to get understanding about what our code is, what kind of improvements can be done. All those things will be discussed a little later. Now it is launched. You can see that the Intel vTune Profiler gets launched, and this is the welcome page for you. It's a very neatly done UI for you. The GUI is very easy to use, and you can see that you've got guidelines available. You can create your project and start your profiling there. You've got recent projects listed there, the recent results listed here, and we have got the help tool, documentation, cookbook, link for everything is available for you, and you have also featured contents highlighted there. You can see all those and you can try it out. The moment you click configure analysis, you'll be able to get into the launch application, and where we have kept the matrix.exe, regular matrix file that we are going to use, and we are going to analyze that file. Now when you click this button, the run button, it runs. You can see that it is running in the background and you are collecting results here, and you can see the status as collecting data. This data can be analyzed and you will be able to understand the performance related parameters which the vTune Profiler gives you. It may take a while for the analysis, so sit back and relax. You will get the results in a couple of minutes, and once it is done, you will get into the complete details. The plethora of information about your application can be really analyzed. So we have to wait until we get the results. It may take a while, and I request you to wait. Maybe first couple of times you may find it a little difficult to understand the flow, but after that it will be really easy for you to get the flow understood, and also you can understand the complete content that the vTune Profiler is going to provide you. All these data, whatever I am talking about, whatever inputs I am giving, all these are available in the user guide. The link can be provided to you as well. So I request you to go through the user guide as well, because it is going to help you in understanding what kind of analysis can be done. Is it algorithm related, microarchitecture related, parallelism related? What is it? It can all be understood very clearly, and I request you to strongly go through the user guide. That's one very important thing. Now you can see that the data collection is completed successfully. Finalizing results is coming in front of you. We are going to get the result right in front of you in next couple of seconds. So once it is done, you will be able to get the summary. You will get the complete summary out here. You are getting it in front of you. The elapsed time, the effective CPU utilization, all these data you are getting. You can see that 97.969 seconds is the elapsed time. Effective CPU utilization is 64.5. You've got a histogram which is going to help you out in understanding things in a much easier way. The total thread count, the wait time with poor CPU utilization, all these details, including much more detailed information about the time factors and the metrics are presented to you. You can see that the collection and the platform info is also presented to you, which has details about the platform, the operating system, all those things. So we are going to go through the next level, where you can see that the bottom up detail is presented, where we have seen something right in the previous discussion. I have explained each of this, the grouping. You can group the data with available options over there. You can filter the data by process, by module. You can also select a grouping level for the timeline bands. You can drag and drop to select a range on the timeline area. You can do that as well. You can restart the help tour if you are using it for the first time. The complete information, whatever I have told you, will come again. You can see that the caller to callee information, the caller to callee details are analyzed and presented here very clearly. And you can see that the total time, the CPU time is presented in front of you. And in the right hand side, we have got the caller and callee followed by that. You've got complete information. You can see the wait count, total, self, function, source file, all these details are, this helps you in analyzing in depth. So now the callers is available there. You get all these details for the callers and followed by that you have callee below that. So you can understand the caller to callee data, how the function call has happened. All those things can be very clearly understood using this. The parameters and the metrics can be understood pretty clearly is what I'm trying to convey. Now we are going to the top-down tree where you've got grouping option available for you. You can go ahead at the call stack option. I'm going to click that right now. This is call stack or source function stack. Both options are available. So you can select whatever you want and you can get that. And you can see that the complete analysis is presented to you. And for the thread, you can add CPU sample, the transitions, everything can be included or excluded based on your requirement. And try this out. Once you try this out, you'll be able to understand. And so all these are very simple and easy to understand. Try it out, and in case you have questions, I'll be able to answer that. Thank you.
Hope this was all new information for you. So I strongly believe that you guys should go ahead and learn all these kind of tools which are available for you to use, and do not just stay theoretical. Whenever you talk about compiler design, whenever you talk about computer architecture, it's really very important for you to know how much more that you can really get out of it. I have given you my email ID as well as my YouTube channel details where I have taught all this stuff. If you have any questions, you can ask me through the email ID that I have provided. You can reach me through email ID as well, and I'll be really glad. And most importantly, please make this subject as a practical one. This is not a theory paper. You should have a clear understanding of what is what. You should have a clear understanding of where I can improve, how I can go ahead and improve. These kind of understanding only is important when you go ahead and compiler design, COA, or even embedded systems to a very decent extent. Now, having said that, if you have any questions, I can take it up right now. I made it very crisp, I believe, and I hope you are all comfortable listening to the demos and reading the demos as well. I would like to take some of your questions. If you have any, you can type in the chat box. I'll be really very happy to answer.
Dear students, feel free to ask some questions.
वो guest lecture है answer attendance नहीं last form भर देते हैं ना last
Manav, if you have a question, you can ask loud. If it is technical, we ran out. Any other questions? Thank you, Dr. Shulinia. Thank you all the other professors who are out here. Really
Thank you. Thank you, Sriram sir. Hope we really had a very good knowledge regarding this parallelism concept. Actually, our students have their laboratory session parallelly for this theory paper, but they are learning very basic things regarding compiler design, about symbol table, LL1 parser construction, LR parser construction. So like that, whatever theory they are learning parallelly, they do have their laboratory. So this is the last module where they would like to extend their research activities in compiler design. So that's why we plan to have this session. So thank you so much, sir. I will definitely share your videos and the lecture materials presentation to our students. Students, kindly leave your feedback, which I have shared in the chat board, chat window, as well as if you have any query, you can ask. Otherwise, you can post it in the feedback form itself. I will discuss with the Sriram sir and get back to you. Here with us, Professor Venkatraman and Suresh sir also here. I feel very thank you for them. Thank you so much, students. Thank you. Sir, I will share the feedback link, all those things to you, sir. Thank you. Students, if you feel free, you can switch on your video. We can have a small photograph. Is it okay, sir? Shall we have one group photo? Is it possible? Just 2 seconds. Shall we have? Sriram sir, shall we go with group photo?
Second, please.
Yeah. Students, please get ready. We can have an photograph. In another 2 seconds, just kindly switch on your video mode. In 2 seconds, we can take one small photograph. Yes, definitely. I will share the class. I will share this recordings to you. Yes, those are ready. Kindly switch on your video.
Not me.
Yes, students, all of you, just 1 minute. We can switch on. We can have one photo. Just 1 second. Yes, okay, fine. Okay, we can have one group photograph. Ready? 3, 2, 1. Smile. Just give me a second because around the 250 students are there. Just 1 second. Yes. Fine, students. Thank you all for your wonderful participation. And I hope you all really enjoyed this session. I will share this recordings to you. Thank you all. Before leaving, kindly fill the feedback form. Sridham sir, thank you so much from Department of School of Computer Science and Engineering on behalf of Dean and our faculty coordinators. I would like to thank very much for you, sir. Thank you so much, sir. Thank you.
Thank you, Professor.